Welcome friends, we will talk about one more application problem on lecture 16. Okay. In this case, we are going to talk about application problem 2. Interestingly, in this example, we will talk about stability of tethers under distinctly high C waves and seismic excitation. So, we are talking about stability analysis which will lead to the safety interpretations of compliant offshore structures. We will take an example again, a tension-like platform. We will examine this under distinctly high C waves and seismic excitation. This is a very interesting study. The study has references cited in NPTEL website. Please look at those papers on relatively the same topic authored by me and my co-authors. So, look at these papers. We are anyway presented interestingly for the safety interpretation. So, as we now agree and understand, the compliant system like TLP where the buoyancy force exceeds the weight by a large number is always compromised by excessive initial pretension on the tethers. So, any variation on this T0 value, which the initial T0 could challenge the stability of the platform. Okay. Why we are re-insisting this statement? It is because of the fundamental reason in compliant structures like tension platform, initial pretension plays a very major role which actually bridges the static components of the buoyancy and the weight of the system. However, when the platform oscillates with respect to its mean position under the action of wave, wind and current, obviously you will see that the buoyancy also changes because of submerged volume change, and the buoyancy changes will incorporate approximate changes or appropriate changes in the tether tension variation, which is dynamic in nature. So, in a given life system of the system structure like TLP, the tether tension variation is going to happen continuously. I would like to see that this tether tension variation caused by extreme wave cases, that is distinctly high C waves in the presence of seismic excitation poses the problem very interesting. So, as reliability actually is bridging the satisfactory performance of a given system under the given load combination under the given conditions. So, we know that reliability is assessment of performance of a system under given conditions. In our case, the conditions are load combinations. For a specified period of time, for a specified period of time, in our case it is going to be the lifetime of the structure. Okay. So, reliability is actually an assessment of the performance of the system under the given conditions for a specific period of time. So, in this present example, we are going to analyze, the objective is to analyze stability of the platform under dynamic tension variations caused by extremely high C waves and seismic excitation. That is what our objective is. Okay. So, of course, it requires a dynamic analysis, we will look into that. Interestingly, you know, extremely high C waves plus seismic excitation is an extreme load combination. Okay. So, this is of course in the study is numerically simulated. One can easily understand that experimentally such waves and such conditions cannot be simulated. Therefore, the study is on numerical simulated model on a TLP. Okay. So, one is interested to know the dynamic response of a system under such extreme load combination using numerical example. So, we will talk about this now. Interestingly, one should now understand the mathematical model of TLPs. Okay. One has to really explain at least briefly the mathematical modeling which has been done for modeling the TLP under the extremely high C waves in the presence of both horizontal and vertical seismic excitation. So, the load acting on the system in our case TLP are 1 extremely high C waves, which is special case. One may wonder that why we are actually doing a reliability analysis for extreme load combinations. Reliability analysis is always assessing the performance of the given system under the given condition. We assume a condition that it may violate, it may challenge the safety of the system, and we are assessing will the system remain safe under the expected conditions. Okay. So, under the normal operating condition, if you look at the reliability analysis, it will always indicate you that the system is safe. So, the unsafeness of the system can always be examined only when the normal operating conditions or the C state is violated to an extreme C state. In the earlier example also, we have taken an extreme C condition. In this case also, we have taken extreme combination where the C waves are extremely high in sense, and the second will be the presence of seismic excitation. Now, the problem is made more interesting because of two reasons. One, the analysis should focus on how to actually simulate or generate an extremely high C wave. So, one should exactly know what do you mean by extremely high C wave. Do we have any equations which can help me to simulate such a C wave? Do we have any ready-made spectrum available in the literature which helps me to generate or simulate extremely high C wave? How literature classifies a C wave to be extremely high, in what sense? So, we should know this first. Secondly, what is the interest of seismic excitation on a compliant system? So, this is a fundamental question asked by every structural engineer to understand the complexity of seismic excitation on a floating system. Now, let us look at this example very clearly here. If I have a system which may be a jacket platform, offshore structure, a jacket platform, okay, or a building, let us say multi-story building founded on piles on a soil subjected to lateral forces. In this case, the lateral force obviously going to be wind. In my case, in offshore system, the lateral force is obviously going to be the wave for the substructure and of course wind for the superstructure. Okay. So, I have again the jacket legs which are battened and laced. Okay. I have a system like this. Now, let us imagine in both cases seismic forces are excited. So, there is a signal which causes displacement of the ground at this point. Okay? There is a signal which causes displacement of the system at the ground point. Okay? Along x, along y and along z. Okay? This is a seismic time history which gives me the seismic acceleration x double dot g, acceleration of the ground along the time. So, it is a time history. Okay? So, if this time history is imposed at the connection points of the columns or connection points of the column members of this building, obviously you will see when the column members or the column legs of the jacket are displaced continuously for over a specific period of time, this induces additional stresses to these members which may cause these members to fail in both cases, in jacket structure as well as in a building. Okay? Now, if I remove the support system, let us say I have a support system let us say I have a support system of a different order as in the case of floating system. Let us say I have a tension platform which of course has the flare boom, it has a helipad, it has living quarters, it has turbo machinery, it has a drilling mast, etc. All topside details as usual, and there are column members and there are pontoon members. There is a top deck of multi-tier, let us say, and now they are station kept or position restrained using what we call as teethers. So, we all know now that TLP is a process by which the buoyancy exceeds the weight by a large amount. Weight acts downward, we know buoyancy acts upward against gravity. Buoyancy depends upon the submerged volume of the system. I have got a very large platform with very large diameter of the member. So, the submerged volume is very high, therefore, the buoyancy force will act in the upward direction, and whereas the W weight of the platform will act in the downward direction. There is a very great imbalance between these two which will be bridged by the initial tension in the teethers. So, tension is imposed on the legs, what we call as initial pre-tension in the teethers called as T0 on each leg. If there are 4 set of legs and each leg will have T teethers, there will be 12 teethers as we normally saw in the previous example as well. Okay. So, now interestingly let us impose the same earthquake signal here along x, along y and along z. Okay, history is imposed. Okay. So, earthquake history means along the time history acceleration is imposed, the ground is displaced by a specific intensity. So, now the question is, we all agree and understand very closely that when the system rests on the seabed or on the floor where it is being founded using a pile rigid connection, obviously the displacement of the ground will get transferred to the support system, which may be a column or a jacket leg as the case may be. Whereas in this case, you know, they are actually teethers or cables, okay? They are nothing but cables. Okay, they are, okay, let me redraw this. They are nothing but cables. So, they do not, they carry only axial tension. Teethers are capable of carrying only axial tension, no compression. Okay. So, if you have any force imposed on this as a compressive force, the cable cannot carry this force. Okay. Now, the system is actually remaining, the top side deck is about, let us say in our case as we saw, maybe about say 600 meters water depth, 1200 meters water depth, 1100, 800 etc. Okay, very deep water platforms. So, when I impose an earthquake signal here which causes a displacement of the ground, it is obvious to have a feeling that how this force or this displacement will affect the behavior of the superstructure. Our whole scenario is to study the safety or stability of the platform when it is connected to the seabed using teethers. When the platform is disconnected and the teethers are not attached, it becomes free floating. Why? Buoyancy exceeds the weight by large amount, the platform will remain free floating. Okay? When I am station keeping it, when I am housing it using a tether set to the seabed, when the position restraint is imposed as a condition to the system, then the system is not allowed to move freely to a larger extent, but the system is allowed to displace because of the action of water and waves and current. When in such situation, when the earthquake signals are imposed, how this will cause an additional displacement to the system, because the system is not directly resting on the seabed, it is only anchored to the seabed using cables. Friends, it is interesting for you to realize and quickly understand that any movement in this direction or this direction will impose displacement. Let us say the system is displaced by this amount. Okay, let us say. Obviously, this position compared to the earlier one will have a change in T0. I call this as delta T0. Delta T0 is change in tether tension. Let us say hypothetically this is purely caused only by the displacement, imposed by seismic forces. Okay, seismic forces. So, the change in tension now affects change in buoyancy and weight, because there is an imbalance between these two. Therefore, the set down effect caused by the submergence and the offset caused by the wave action in combination with seismic action changes buoyancy. Okay? The change in buoyancy will cause change in tension. Therefore, earthquake signals are imposed indirectly as change in tension in the whole system. You understand? Change in tension is what we call dynamic tether tension variation, which causes imbalance. Now, my worry is, under such imbalanced condition, when the dynamic tension is imposed by the earthquake signal in the presence of distinctly high sea waves, will the system remain stable? Okay, is it safe? That is the whole question asked here. That is a problem formulation. You understand? That is how we are imposing the problem to the system to find a solution. Is it going to remain safe? So, the reliability of the system under extreme load combinations of distinctly high sea waves in the presence of seismic excitation will make the system safe or unsafe when the system is performing its operation, for example, drilling. Okay? So, both horizontal and vertical seismic excitation should be imposed at this connection point to the tether. So, seismic forces imposed at the bottom of each tether will cause an axial force additional that makes the tether tension imbalanced. Okay? I am only looking at the unbalanced or dynamic tension variation imposed on the T0 value, which is essentially caused by the seismic excitation in the presence of distinctly high sea waves. Okay? That is when the hull is under offset condition. When the hull is in static equilibrium, we are not bothered. When the hull is under offset condition, which is caused because of the wave force acting on the lateral direction, under that situation, when seismic excitation also happens, will it cause a worrying factor on dynamic tension variation, which will challenge the safety of the system while performance. Okay, that is where reliability is being seen. Therefore, the tether tension variation caused by the seismic excitation should remain non-linear. Okay, so, we first qualify a spectrum which can give me the acceleration of the sea quake or seismic excitation at the seabed. So, we use Kanai-Tajimi spectrum for this. So, seismic excitation is imposed using or generated using Kanai-Tajimi ground acceleration spectrum. To do the analysis, we need to of course make certain idealizations. So, following assumptions are made in the analysis. 1. Platform is considered as a rigid body. Having 6 degrees of freedom. The degrees of freedom are marked like this. So, this is my x axis, this is my y axis, this is z axis. This is surge along x axis, this is sway along y axis, this is heave along z axis. These are displacement degrees of freedom. You keep your thumb towards the direction, remaining 4 fingers will mark a direction. I call that as rotational degree of freedom. So, about x it is roll, similarly about y it is pitch, similarly about z it is going to be yaw. So, 3 displacement degrees of freedom and 3 rotation degrees of freedom at any point, which is obviously going to be the center of mass of the system. So, the platform is considered to be a rigid body having 6 degrees of freedom. The second assumption made is water waves generated due to ground motion are neglected. Okay. So, only the ground motion purely imposed by the specific excitation, and water waves are only because of the wave loading caused by the distinctly high sea waves. Okay. The third assumption made is the hydrodynamic force coefficients which are the drag coefficient and the inertia coefficient are same for pontoons and column members, and they are independent of wave frequencies. Fourth, the Cm value, that is the hydrodynamic inertia coefficient, is considered to vary along the water depth. Okay. So, Cm values at the seabed, at the middle depth, and at MSL, that is mean sea level, are taken as 1.8, 1.58 and 1.5. The variation between them, variation between these segments, variation of Cm in between the segments, okay, are modeled by a second degree polynomial fit. Okay. The next assumption is about the stiffness of the tethers, axial stiffness of the tethers, which we all know it is AE by L. Okay, is modeled like this. So, the stiffness axial of the tether is given by two cases. One is equal to AE by L if the elongation is greater than 0. It means from the initial condition it is elongated. Otherwise, it is 0 if the elongation is less than 0. That is, tethers under slack condition are not considered. Okay. The initial pretension reduction when the teethers become slacked is not considered. Okay. So, as I said in the beginning, in this problem we have to discuss two things. One is the seismic force acting at the seabed, two is the distinctly high sea waves. What do you mean by distinctly high sea waves? So, shape of distinctly high sea waves is quite interesting for this problem, is crucial for the given sea state. So, to support this there are experimental investigations conducted by various researchers to qualify a sea state or a sea wave to be called as distinctly high. Okay. They are done by or conducted to classify distinctly high sea waves. How they are classified? Okay. Kim et al. 1997, Kribel and Alsina. So, one can look at these papers to know more information about how to qualify or how to classify a given sea wave as a distinctly high sea waves. Okay. They stated that the shape of these waves in sense distinctly high sea waves of these waves is steep. That is the first observation they have made. Secondly, they are asymmetric with respect to both horizontal and vertical axis. So, your wave should be asymmetric to both horizontal and vertical axis, at the same time it should be steep. Now, the question is, when will you classify a wave as a steep wave, okay, and when you will be able to generate a wave which is asymmetric with both respect to horizontal and vertical axis, that becomes a question. If I am able to generate a wave which is steep and remains asymmetric about both these axes, I can call that wave as distinctly high sea waves as stated by Kim et al. And Kribel and Alsina. Okay. So, the problem now is how to simulate such a wave which will be qualifying distinctly high sea wave with the help of experimental studies conducted by these gentlemen. That is the argument now. So, therefore, one can always say the experimentally simulated sea waves is always pertaining to a limited boundary condition. Okay. In the real sea state, the such simulated waves may not be able to simulate the same effect as on the real sea state, because experimental investigations are done on a scaled model, therefore, there may be a limitation. Okay. So, what we are interested is to understand the effect of sea quakes or earthquakes in the presence of distinctly high sea waves in the real model. Therefore, I must be able to simulate both with a numerical system, not with the experimental studies. Therefore, Zhou and Kim in 2000 developed a numerical model, okay, a numerical model to generate freak waves. Based on the design spectrum. Which can result in distinctly high sea waves. So, that is one solution we have from the literature. Instead of going for a simulation which is done experimentally by the gentleman, which helps us to qualify a wave as a distinctly AC wave, this gentleman gave us an alternate method using a numerical model to simulate a wave, which can also be called as a distinctly AC wave, because they qualify the same manner as that of the conditions stated by these researchers at the different time. Okay. In the present study, therefore, now we will say in this study, in this example, C waves will be generated using modified PM spectrum. Interestingly, one may ask a question, sir, PM spectrum is actually a standard spectrum which is used as a design spectrum. How will we be able to generate a wave which can qualify to be called as a distinctly high C wave using a standard conventional PM spectrum? That is why I said modified spectrum. So, to release this doubt from your mind, we will generate a spectrum using Pearson Moscow spectrum modified with one parameter. We will then generate a time history from that. Then from the time history, we will check whether this wave is really steep and is it having asymmetricity both about horizontal and vertical axis. If this condition is satisfied in the given enlarged time history of the given simulated wave using the spectrum, then my condition of generating or simulating a distinctly high C wave is satisfied. Okay. Now, the distinctly high C waves is generated using nonlinear wave kinematic theory. So, when you generate a wave using nonlinear wave kinematic theory, following factors are very important, because I have to qualify the wave first as a distinctly high C wave. So, what are those factors which are important? The factors that are important one, nonlinear wave theories tend to become overly complicated, okay, that is one issue. Nonlinear wave theories tend to become highly complicated when a low order approximation is used. Okay, as stated by Jung 2006. Therefore, several researchers have simulated distinctly high C wave successfully using simple Airy's wave theory. So, several researchers by name Pilato, (2002), 2003, 2003b, as you can see from the list of references given in the website of NPTEL for the specific course, they have simulated distinctly high C waves using Airy's wave theory. And the force using Morrison equation, because the system is compliant. Water body kinematics is used or generated using Airy's wave theory, and the random generated sea surface elevation using PM spectrum. So, this condition is like this. Airy's wave theory for water bottle kinematics. And sea surface elevation using modified PM spectrum. That is what we have used, which I will show you now. Okay. Now, what is the modification done on the Pearson spectrum? Okay. This modification suggested by Mitchell in 1999. The original PM spectrum which is a function of wind velocity is modified. Is modified as a function of modal frequency that is the first modification done. Secondly, it is further modified as a function of significant wave height and modal frequency Now, the modified one parameter equation is given by this following: S eta eta omega, the spectral function is 8.1 10 power minus 3 g square by omega phi exponential minus 1.25 omega m by omega to the power 4. Call equation number 1. Where g is acceleration due to gravity, okay, in the equation. Omega m is the modal frequency. In this particular simulation, it has been taken as 0.46 radians per second. That is nothing but 0.07 hertz. S eta eta is this power spectral density function of the wave height. Eta, that is the sea surface elevation. Now, the wave elevation, which is eta of t, is now realized as discrete sum of many sinusoidal functions. Of course, when you do the discrete sum, it should have with different angular frequency and random phase angles okay, that is very important. So, eta of t is given by a discrete sum of different waves of sinusoidal function which satisfies this equation equation 2. Where ki is what we call as the wave number, omega I is the discrete sampling frequencies, which means delta omega I is given by omega I minus 1. I will keep on generating the wave like this, sampling frequencies. N of course the number of data points, and phi I is the random phase angle. Now, interestingly, what should be the condition satisfied? The condition to be satisfied is, which is very important to make this wave as distinctly high C wave. The generated wave profile should have a peak at a particular time t0 which will be distinctly high. In comparison to other wave heights and therefore, I can classify this as a distinctly high C wave. Okay. So, one has got to be very careful to choose this particular time t naught where the wave elevation is going to be distinctly high. So, interestingly, the problem has got two classifications. One is to generate a seismic spectrum or seismic excitation using Kanaitazimi spectrum. Other is to generate or simulate numerically a distinctly high C wave, because experimentally simulated waves cannot be useful for a numerical study of 1:1 scale, is very difficult. Okay. So, we have used Airy's theory and modified PM spectrum to generate a wave, which I will show you in the next presentation, in the next lecture, how the wave has been generated. So, the wave should have steepness plus wave should show asymmetricity both in horizontal and vertical axis. Okay. So, we will discuss this continuing in the next lecture. Thank you.